Hi all, we're going to spend the next two lessons talking about implicit differentiation. So you may remember that where you have functions that have x and y in them and you want to find dy dx. So if you want to get yourself ready for notes, we are going to be looking at this first problem set from 3.6 in this lesson, and then we'll have another one from 3.6 for your next lesson as well. So let's get started. One thing you might remember about implicit differentiation is you can kind of treat it like the chain rule. What I mean by that is that if we have a function here with x, that's fine. We're used to that. But if we have something like a function containing y, such as y squared in this example, when we take the derivative of that, so d dx, in terms of our x variable, so we've got these two that don't match here, what you end up with is the derivative of that y function times dy dx. Some of you might write this as the derivative of the function using y times y prime. And that's just fine. Here is a way to think about why this works using the Leibniz notation, which is where you're using dy dx, versus the Newtonian prime notation. So the reason that this works is basically you can't take the derivative here because these two variables don't match. So maybe you remember from last year that in order to differentiate or integrate, your variables have to match. So what we are allowed to do is, if I have a term, I can then just add on dy over dy, since that is the equivalent of multiplying by 1. Now, I can also reorder terms when I multiply. So that's all I've done between these two lines. Now I have dy dx and d dy. Now the great thing here is that these variables do now match. So I can just drop that straight into our f prime. And as we discussed, dy dx is the same as y prime. So here's another way to illustrate why that works. And now let's look at a problem with how to use it. So if x squared plus y squared equals 25, find dy dx. So what we're going to do is take the derivative dx of both sides of the equation. Just following our basic rules, if we treat the equations the same on both sides, it's just fine. Now, since we have two added terms, we can split those apart even farther because we're allowed to differentiate terms separately. So this first one, the derivative of x squared in terms of x is 2x. The derivative of y squared in terms of x, we're going to end up with the derivative in terms of y, of the function in terms of y, so that would be 2y, times y prime, or the derivative of y dy dx, is equal to the derivative of 25, which is 0. Now, since we're looking for dy dx here, this is what we want as our final answer. That's this term here. We need to solve for y prime. And from this stage, we're just going to do our basic algebra. We're going to subtract 2x from each side, and then divide by 2y to get our y prime term by itself. Here, I'm just going to cut to the chase a little bit with simplifying by 2, and we end up with our final answer of dy dx, or y prime, as negative x over y. Like so. So let's look at another example problem. Here, find the equation of the tangent line on the curve above at the point 3, 4. So here's the curve that we just used, and if we remember, y prime is equal to negative x over y. So we're going to be doing the same thing that we would for any other tangent line. We're going to start with our point slope form, and you'll notice I wrote dy dx as the slope. And remember, this is one of the reasons that it is it's the difference in y over the difference in x, which is our definition of slope that we've been using since our first algebra class. Then we'll plug in our points. So y minus the y value, which is 4, is equal to x minus the x value, which is 3. And then we'll plug in our slope using this formula here. negative x over y. So negative, the x value is 3 and the y value is 4. If you want to leave it like this in point slope form, that's just lovely. You also might be asked to convert it into a standard form where we would multiply everything by 4, distribute the negative 3, and then add the 3x and add the 16. So this would be the standard form that you might have to place your answer in. Let's look at our final question. So find y prime if sine of x plus y is equal to y squared cosine x. So here's an example where we have the chain rule on one side and the product rule on the other. So I'm going to start just like we did before, where we're going to take the derivatives of each side and we're going to do those separately. So let's start with sine of x plus y. If we're using the chain rule, this would be our f function, and then these two together are g. So then f prime would be cosine, and g prime would be the derivative of x, which is 1, plus the derivative of y, which is 1 for the derivative of y times y prime, because it's using implicit differentiation. So plugging that into the chain rule, we have f inverse, so cosine of g, x plus y, times g inverse, which is 1 plus y prime. So that's the derivative of the left side. I'm going to erase that to use this space for the right. So on this side, we're using the product rule, so we have y squared times cosine of x. Now cosine of x is in terms of x, so that's just going to be the derivative negative sine. Here, just like in the last problem, we get 2y times y prime. So when we use the product rule, we get 2y times y prime for f prime times g, which is times cosine of x, plus y squared times negative sine of x. Now, here's where it becomes a little bit trickier. This is our long derivative here, which is accurate, but you'll notice we have 2 instances of y primes, so we have to do some algebra. The first thing I'm going to do is take the cosine of x plus y and distribute that to here, and I'm going to do a little bit of simplifying on the other side. Now I know my handwriting got a little bit rough there at the end, but hopefully you're following along in your own notes. So the next thing I want to do is I want to get my y prime terms on the same side. So I'm going to subtract the y prime term from this side to get these two together, and then I'm going to subtract away the cosine of x plus y to the other side so that I have a y prime side and a non-y prime side. So now we have our y prime terms on the same side, and now I'm going to factor out y prime by itself times cosine of x plus y minus 2y cosine of x. And now we have a single y prime term, and we still have this right-hand side that doesn't have any y prime terms. And the last thing we're going to do is divide both sides by this whole factor here to get y prime by itself. And there you have it. Y prime is equal to this large rational function. Please let me know if you have any questions about this first lesson of implicit differentiation in the comments below, or if you've got more questions than that, please grab an appointment slot for later in the week. I'll talk to you later.